It's my pleasure to welcome the second talk of today. Arno Pauly is going to speak to us about Luzin Zen and randomness reflection.
So thanks, Linda. So I am giving a talk about stuff that has appeared in print now, so it's not particularly fresh, but I kind of wanted to talk about something that has actually that has randomness in it, and I don't have that much to choose from them. If you do want to know what I have been up to more recently, you heard a bit about that in Linda's talk yesterday, and Giovanni is going to tell you more about that later today. And hopefully, if you have heard me talk about this before, it wasn't too boring then, and you had some time to forget details, so maybe there's some interesting things. This is a project that I feel fits very well within the sort of philosophy of the field, as Lutz mentioned it earlier. We take some stuff in sort of classical math, maybe analysis, maybe measure theory. We get together with some friends. We put in Turing machines and computation in it. We have fun. We get a beautiful theory, and that's great. So that's what this is about. So I'll start with sort of what is Luzin's N, why is this randomness reflection, and so on. Talk a bit about what goes into the kind of proofs of the sort of main characterization that we get. The main thing is going to be about higher randomness notions, and then I'll tell you sort of why this is, why I have to talk about higher randomness here, why I couldn't do it any way else. And we'll probably later get to some of how this whole stuff is connected to questions like when do two probability measures have the same null sets, when do they have the same Martin-Löf randoms, and so on. Okay, so what is Luzin's property N? Well, that is just a rather natural one. A function from the reals to the reals has Luzin's property N. If whenever you look at a null set, that null set gets mapped by that function to once more a set which is null. Unlike what Linda was talking about yesterday, in this project we do get away with completely ignoring counter space unit interval reals. That all looks the very same. Local compactness and so on does show up at times, so sort of don't replace things by bare space, but otherwise it's sort of mostly not too important what we are looking at. All right, so if you think about sort of this mapping null sets to null sets, that at first may seem like a sort of very obvious thing nice functions should do. And we'll say stuff like polynomials and so on, all obviously to do that. On the other hand, if you then go into the old, you could just think about counter space anyway. Stuff like projections obviously don't. So there are nice functions that have the property. There are nice functions that don't. And we are only really demanding that null sets go to null sets. So this could happen because the function is sort of measure preserving up to some scaling or so, but it doesn't have to. It can just sort of do very weird things with positive measure things. However, it would want just null sets need to go to null sets. All right, so how is this related to randomness? Well, what's a null set? Well, a null set is a set which is contained in everything which is in the set of all points which are not Martin-Löf random relative to some particular fixed oracle. So we can just translate this into saying, well, Luzin then means that for any oracle P, there exists some oracle Q, such that whenever the value of the function is Martin-Löf random relative to Q, then the point where you started with has to be Martin-Löf random relative to P. So the Q could obviously be sort of much higher than that P, but you know that if your function value looks very, very random, wherever you started to get there must have been random too. We would like to have that be nicer, and we would probably just look at computable functions F. And well, what would nicer mean? Well, one thing is that rather than having sort of two randomness notions here, we may just want a level of randomness where actually we can tell, oh, if the function value is random in this particular sense, then the input was already random in the very same sense. That would be the sort of nicest thing we could probably ask for. We would definitely want to know something about, oh, how much worse than P would that Q need to be? Can we bound that somehow? And finally, the question is, do we really need to check for all of those levels of randomness, for all oracles P, that random stuff only comes from random stuff, or can we get something of the form, oh, since F is computable, if it fails for some oracle, it already fails here. So what are the kind of things that we could find before we start thinking about this? On the one hand, Luzin's N is a pi11 complete property for continuous functions. So I mean, it's a complicated property. It's not as horrible as it could have been. But yeah, looking at the constructions, it doesn't really get us far because those constructions, in a sense, are too nice, too uniform. You don't really get anything meaningful about what they're doing to the random points here. But that just tells us, okay, what is the level of niceness that we can hope for? And well, it's sufficient to check this for sets which are actually compact, and here is sort of where the local compactness of the kind of spaces that we may want to work with go into. Compact sets obviously have the nice properties that if we are looking at a computable function, the image of a compact set is once more compact, so it doesn't go up too far. Okay, so what happened? What did we find out? So this is sort of, well, you could just take this all for computable functions, but actually going all the way up to effectively program measurable functions, which would mean that basically you can uniformly compute f of x from the alpha's jump of x for some computable ordinal alpha. That's good enough to get all of those things, and as we will see later, even for computable, we can't see more. Okay, so Luzin's N. Now, this oracle Q that we just got in this existential quantifier, that's essentially all. You can always just pick that delta 1 1 in what you started with. So if you do want to and then basically, since delta 1 1 or of delta 1 1 is delta 1 1 of whatever that you started with, we just get that. Well, if a function is reflecting delta 1 1 randomness relative to any oracle, that's Luzin's N. So that's just what's happening. How mapping null sets to two null sets work, you would need to know that the pre-image of any delta 1 1 relative to stuff random is the delta 1 1 random relative to the very same stuff. We can actually get rid of this overall quantify overall particular oracles. So, for example, reflecting pi11 randomness is all that you actually need. So if you do know that whenever the function value is pi11 random, then the input was pi11 random, sufficient and necessary to get it for all higher oracles. We can use the delta 1 1 relative to some oracle characterization, and we can see that using Kleini's O as that oracle, that one oracle already gives us the very full strength that gives us. That's for all potential oracles. But of course, the sort of dream would be if you have something like, oh, if this works for all oracles, then it's fine. Is not that you can say, oh, it's fine if I put in Kleini's O. No, you actually want to put in something computable and make the oracles completely go away. That would be the great thing to have. Well, we didn't get there. So reflecting just delta 1 1 randomness is true. That happens, well, because you reflect delta 1 1 randomness relative to any oracles. In particular, you do it relative to 0. And there is another property that just falls out of this whole characterization, which is that a function from reals to reals that has Luzin's n can only sort of must have that almost all fibers are countable. You can't have too many points whose pre-image under that function is some uncountable set. And reflecting delta 1 1 in O randomness is enough to prove that holds. Without sort of just reflecting delta 1 1 randomness, we don't know where to get that from. But if we put that in as an extra criterion, we can get to the point where we can then say, oh yes, having almost all fibers countable, reflecting delta 1 1 randomness, that means you do reflect delta 1 1 randomness relative to any oracle. One characterization would be there's a uniform procedure to compute f of x from the alpha's jump of x for a computable ordinal alpha. But yeah, basically, if you prefer just replacing this by computable, you get a weaker statement, but that still works. Reflecting delta 1 1 randomness, that means you do reflect delta 1 1 randomness relative to any oracle. One characterization would be there's a uniform procedure to compute f of x from the alpha's jump of x for a computable ordinal alpha. But yeah, basically, if you prefer just replacing this by computable, you get a weaker statement, but that still works. Yep. If not, they don't deserve to hear the talk. Okay, so now that I've been interrupted by my own past self, I did answer your question, did I? Okay. Yeah. You have to get
Arno, Arno, would you mind repeating the questions that come during the talk so that the Zoom people hear them as well?
Okay, yes. I'll try to keep that in mind for next time. Yeah, so the question Philip was just asking is whether having here Martin Löf random, what would sort of so that you have Martin Löf random relative to any Pi11 oracle, whether that's good enough. Yeah, yeah. Yeah. Yeah, I mean, well, those should coincide for delta 1 random, but I can't quite do the computation on the fly whether sort of doing that detour whether you actually do get it just on the Pi11 randomness level, also the Martin Löf version, or whether you would need to push up a little bit beyond there. Okay, so right, sort of why, first of all, sort of why does higher randomness start showing up here? Well, that's basically because you're taking images under a continuous function, which is going to get you up rather quickly. If you take a sigma 0 to null set, the image of that under function having Luzin's n is going to be a sigma 1 set, which is again null. So sort of hence you have these jump up from the low levels to the high levels just happening. Yeah, that's how you can move rather easily from here to here, and then since you have it for all oracles, that's actually a sort of more specific statement than what we had on the previous one. But yeah, so then the whole sort of the difficulty is seeing how can we make sure that reflecting randomness on one particular level already moves us up. We can also get Kurtz, a kind of Kurtz random characterization of the very same thing. It's once more we want delta 1 in O Kurtz random for that, and here we actually do know whether or not the O is sort of necessary for it to be true or just necessary for us to be able to show things, because reflecting delta 1 Kurtz randomness is a sigma 1 property. Luzin's n is a Pi11 complete property, so hence reflecting delta 1 Kurtz randomness is something different. I don't know what it is, but it is something different. Okay, I had sort of mentioned it doesn't really matter too much what kind of space you are looking at. There is a bit of sort of sanity constraints that you do need, because if you're sort of willing to just restrict yourself to sufficiently weird subsets of the unit interval and you're sort of making some additional set theoretic assumptions, we can sort of violate this property of having that almost all fibers are countable. So you can then go and build a function essentially defined on a set A, subset of the unit interval, which is computable on A, which maps A to a non-null set. the function has Luzins n, so null sets get actually mapped to null sets, yet every fiber from the image of that set A, and that was a non-null set, is not countable. You basically do this by an inductive construction over a suitable well ordering of the reals, and then you sort of need that sort of certain cardinals from the key Jean diagram are just equal, so that at any step you can still do what you need to do at that step in order to build this set A. Here obviously it's sort of here it's obviously going to be very relevant whether you say non-null or positive measure, because what you're getting here is not going to be measurable or anything like that. So go to sufficiently weird spaces and stuff stops working. Okay. What kind of higher higher randomness do you sort of need to make these things happen? One thing that we needed was a result which is essentially saying that if you have something which is not very random, then it's not going to be hyp-computable from something that is very random. So that's what the theorem. You pick some oracle z, which is going to characterize what very random is supposed to mean. And now you start with the y, which is delta 1, 1 in that random, and it's also pi 1, 1 random. Depending on what that is, that might come for free, or that might be an extra constraint. Now, if you have some x, which is just plain delta 1, 1 random, and it's hyp-computable from y, that whole thing must have already, then x must already be delta 1, 1 in that random. That's something that Joe Miller and Julian showed for normal randomness, normal Turing reductions, and so on. And we could mostly get the proof of this theorem by sort of following step by step what they were doing and replace Turing by hyp and stuff like that. The only exception is that the sort of pi 1, 1 randomness shows up as a new fresh thing, and that is that assuming that y is already pi 1, 1 random is making sure that if you're looking at how hyp reductions work, you don't need to worry about x being computable from an alpha's jump of y, where alpha is a y computable ordinal. You just can take alpha to be a computable so that's why you want this pi 1, 1 randomness constraint in the for the proof to work, and we actually have an example that's showing that if you would delete the pi 1, 1 randomness here, then it's actually false. Right, but if your oracle that is below Clini's own, you don't need to write that extra. You just get that, well, something which is delta 1, 1 random, which is hyp-below something delta 1, 1 in that random is already delta 1, 1 in that random. And that's how reflecting delta 1, 1 randomness relative to one particular but sufficiently big oracle can move it up all the way. No, you need above O, because then here I'll say if y is delta 1, 1 in O random, then it's already pi 1, 1 random for free, so you don't need to. That's that extra part. Okay, we also need Friedman's conjecture, which was turned into a theorem by Martin. So if you have a delta 1 1, if you have an uncountable delta 1 1 set, basically with something similar to the e-pointed property we heard in some talks before, meaning that everything in your set can compute can compute a delta 1 1 code for that set in a uniform way. Well, then the set is uncountable, then it must be sufficiently complicated that it contains at least one thing which is hyp above O, and being hyp above O means that you can't be delta 1 1 in O random. And that is where the countable fiber is coming from, because now we know that if you have a computable function which is reflecting delta 1 1 in O randomness, then for any delta 1 1 in O random function value, we know that the pre-image must be countable, because the pre-image f minus 1 of my, well, that is a delta 1 1 relative to y class. Everything in it uniformly computes y. We follow along f. So if it were uncountable, it would contain something which is not delta 1 1 in O random by combining these two things above, which would mean that it does not actually reflect delta 1 1 in O randomness. So by this, we actually see that Friedman's conjecture does give us a maybe non-obvious consequence just in classical analysis, because that tells us that, well, if a function maps null sets to null sets, then almost all fibers must be countable, which isn't surprising, but which is probably not obvious either. You can get there easier. This is not the easiest way of doing that. There wasn't any need to put in randomness in order to get it, but yeah, you can get things that you can sort of find in the randomness literature. Had algorithmic randomness been developed before classical analysis, it would have been useful for developing classical analysis later. Okay, so just sort of one more slide on the sort of whole countable fiber thing. Here, what we get is, well, is that any delta 1 1 in O random fiber is actually countable. But just by looking at sort of how countable versus uncountable works as a property of a fiber, well, the sort of the set of all y for which the corresponding fiber is countable, if that set has measure 1, then it actually has to contain all of the delta 1 1 random wise, just because of looking at complexities of the set and so on. And just one final observation, which is linking the whole reasoning about fibers part to this about countable fibers part and why we have hyp reductions showing up. Well, if you've got a countable fiber, then everything in that is hyp equivalent to that function value, because, well, it's a countable pi01 relative to y set, and hence everything in there is hyp in y, and conversely, by applying the function to anything in that fiber, you would just get y back. Okay, so yeah, and then these are the parts, you put them together, and just going to the theorem again, and then you get this. So that's telling you sort of why higher randomness is showing up. This is, of course, not saying anything about do we really need it, or how about just reflecting margin left randomness? Maybe that would work, or something like that. Yeah.
So obviously really wrong. Do we know anything about that? Is it forced to be measured for observing?
No. To have the Luzins, and you really don't need to be measured. Preserving, you can do all kinds of weird things to the positive measure stuff.
Even keeping the fibers count.
Well, having almost all fibers countable is not going to do. If you really want all fibers countable, I don't know straight right now. Right. So that's the next part, and probably I'll have to skip a little bit. All right. So we can't get any very nice and simple randomness notions in set. That I can know for sure. And the sort of way we get there is by just constructing a function, like a computable function, which is essentially going to be very nice and well behaved on non-random points, and which is going to violate Luzin's n by mapping null sets to sets which are not null. Right. So we are starting with a pi01 in zero jump set. Okay. Right. So we have a pi01 in. What's wrong? But here, pi01 in zero jump set here, and we will build a computable function f, which outside of that set is just piecewise linear on any local part, but there are null subsets of this set A, which get blown up to something which is sort of approximating the measure of A. And if you instantiate this with, say, a positive measure pi01 in zero jump set, which is consisting only of, say, Martin-Löf randoms or weak 2 randoms, or even Martin-Löf in zero jump randoms, and that's all something that you can do. Then the function that you build here, well, since it's piecewise linear locally on any non-random in the sense here, it will map it to a non-random in the very same sense. So it can't violate randomness reflection because simply it's nice on all of those, not those non-randoms, yet it doesn't have Luzin's n because on a bunch of randoms it can increase the measure rather bigly. The basic idea is you're building your function, and now you are contemplating where you currently believe that your pi01 relative to zero jump set might be. Obviously, you don't know where it actually is, but you have conjectures at any point about where it is and where it is not. You just leave what you currently have B where you think that A is not. And if you believe that you have a part, say here, that might be part of that set A, then you take what you have here and you add a zigzag like this here. And you keep doing that. Now, anything which is not part of that set A, from some point onwards, you will have some open neighborhood of it where you stop believing that it might belong to A. So you stop doing things to it, you just get something piecewise linear. If you actually, in A, you believe infinitely often that something belonging to A is around here. So you keep adding these things. And then by, for example, always picking the first third of these intervals, that's how you get that set B by increasing things very much. That's a rough idea. If you actually want the details, it ended up taking a couple of pages to actually make everything work out properly. So you need to obviously make sure that you're accounting for measure correctly, and depending on how much you've already said about your function f, you may have to make much smaller spikes because you can't make big spikes anymore and so on. Okay, but the way this function is built, it is nice on the non-marginal of relative to zero jump randoms, but it doesn't. It would, for example, not reflect weak 3 randomness. So this kind of thingy is only separating very low randomness notions, very low randomness reflection notions from Luzin's n, but not the higher ones. And well, anything working along similar ideas can't do better, because something like, oh, where is a given computable function piecewise linear defines the sigma 0,1 in the zero jump set. So any kind of construction that is separating, say, weak 3 randomness reflection from Luzin's n, if you want to sort of, you need a more complicated reason why that function is mapping non-weak 3 randoms to non-weak 3 randoms. Just being piecewise linear there can't work. Something like locally by Lipschitz, same thing. It's a sigma 0,1 in zero jump property. You need something better. And just construction-wise, it's sort of not too difficult to see how to basically make it violate Luzin's n. You just put all of those spikes in there. But this question of how do you get something which is very messy yet nicely behaved on the non-randoms, I don't know. That's one of those reasons why we stopped there and have basically the range of open questions. On the one hand, is delta 1,1 randomness enough if you try to push down a bit what works? On the other hand, we can ask, wait, can a computable function map everything which is not weak 3 random to a null set? Doesn't even have to be the non-weak 3 randoms, just a null set. But at the same time, fail Luzin's n. So you want some other null set, which is not the non-weak 3 randoms, mapped to a set which is not null. And then obviously anything between weak 3 random and delta 1,1 random is also open. I'll actually not tell you what bounded variation and absolute continuity is, but just point out that if you restrict yourself to functions that have a variation which is bounded, then being absolutely continuous and having Luzin's n coincides. Absolute continuity is a much simpler property. So for bounded variation functions, we can just say more. And there, we get, for example, that week 2 random works, Kurt's relative to zero jump randomness works, delta 1, 1, and 0, and randomness obviously still works. And we get something similar as we had previously, where sort of any sufficiently big oracle is fine. And here, for example, any oracle above zero jump random makes it work for any oracle above zero jump, just makes Kurt's randomness reflection relative to that oracle characterize Luzin's n for functions of bounded variation. Small remark here: bounded variation is something which sort of can be effectivized as well. So basically, you have a computable function can have bounded variation without having a sort of computable witness for that. The computable witnesses are not needed here. So this is just a function which is computable as a continuous function and happens to have bounded variation as well. Reflecting Martin-Löf randomness here is sufficient to have Luzin's n, but it is not needed. So you can have a computable function of bounded variation, can have Luzin's n, yet fail to act nicely on just the Martin-Löf randoms. Okay, the reason why I've skipped over that a bit quickly is that I wanted to talk about the relationship of Luzin's n and the absolute continuity of probability measures a bit. So, well, being absolute, a measure is absolutely continuous with respect to some further measure. If anything which is a null set relative to the second measure already is a null set relative to that first measure. And well, say if you've got an increasing continuous projection from the unit interval to the unit interval, well, we can basically take the push forward of Lebesgue measure under that function, get a new probability to measure, and if we started with a function that has Luzin's n, the new measure that we get is absolutely continuous with respect to Lebesgue measure. If we start with something which does not have Luzin's n, well, then it's mapping a null set to a a set which is not null, and hence is creating something which is going to be not null for mu, but that was null for Lebesgue measure. Conversely, if you start with a non-atomic probability to measure, you can look at its cumulative its cumulative distribution function, and well, that's increasing surjection, which has Luzin's n if and only if the measure that you started with was absolutely continuous relative to the Lebesgue measure. So we can just take that and translate what we have to sort of get some statements about computable probability to measures, and basically when its randomness notions coincide with the standard ones, and when its null sets coincide. So having the very same null sets as the standard null sets, well, forces delta 1, 1, and 0 randomness to coincide, forces weak 2 randomness to coincide, forces Kurtz and zero jump randomness to coincide. But of course, these are all rather odd randomness notions. So maybe you want to know what's happening for the more familiar randomness notions, how it's related, whether two probability measures have the same null sets and whether they have the same randoms in that sense. And that's something that and Wolfgang Merkle already figured out quite a while ago. For example, they constructed a computable probability measure, which is mutually absolutely continuous with respect to the standard measure. So the mu null sets are exactly the sets which are just null in the standard sense, but you do get a different notion of multi-left randomness here. You get a different notion of Schnorr randomness. You do get a different notion of computable randomness here. I would kind of try to describe the construction by thinning out a probability measure around omega in a way that de-randomizes omega, but sort of doesn't introduce any new null sets. And well, that tells us straight away that, well, even if you restrict your consideration to the nicest possible functions, having Luzin's n can't give you any low randomness reflection notions just by that kind of thing. There is sort of one more separation. It turned out that, well, in the conference paper here, Laurent and Wolfgang, I think left open the question what's happening with Kurtz randomness. And so we went and built an increasing projection from the unit interval to the unit interval, which is not absolutely continuous. So it is sort of increasing very much in some places, yet any pi01 set which is null is mapped to a pi01 set, which is null once more. So basically you're again adding spikes in very kind of your I mean, you can't do spikes here because you want something which is increasing. But kind of now you would change to something like this here, which is sort of making the increase very much localized, and you want to make sure that you are that you at some point stop putting these increases at the places where pi01 null sets might be, because well, those should not be turned larger. So that gives us again with the very same translation that there is a non-atomic computable probability mu such that mu Kurtz random and Kurtz random is the very same notion, yet mu is not absolutely continuous with respect to the measure. It turned out we could have saved us a little bit of time because in the journal version of that very same paper, Laurent and Wolfgang already sort of showed the very same thing, except that this one here is the other way around. So they constructed something which is where mu Kurtz random and Kurtz random coincide, but right. So yeah, we have destroyed null sets, they've added null sets. But yeah, so sort of combining those, we can say, okay, the Lebesgue measure isn't sitting in a sort of extremal spot of things that agree on what Kurt's randomness is. You can have more null sets than just the null sets and agree on what Kurt's randomness is. You can have fewer, and you can probably have other things as well by just doing some kind of linear combination things. But yeah, so basically, if you're restricting your functions all the way down to increasing surjections, we know how randomness reflection works, how that's related, how those notions work together. For bounded variation, we have a rather clear picture. Basically, there things that are going to be nice start being nice for bounded for functions that have the property of that variation is bounded. If it's not going to be nice ever, well, then obviously it's not going to be nice. But there's this question of if you're not restricting your functions beyond being computable, there's just this whole range of randomness notions where finding separations between them and Luzin's n probably needs some kind of other kind of constructions than the ideas that we had so far. Yeah, as I said, this stuff is already in print and has been online for a long time now. So if you want to read up on anything here, that's it. And that's the point where I stop talking.
Thank you. Any questions? We already had several during the talk.
What was in the chat was, I think, all
Yeah, nothing,
previous.
no question in the chat. I have a question. Arno, have you got any opinion concerning the open question of whether that Luzin's n is equivalent to delta 1,1 randomness, reflecting delta 1,1 randomness? Or is that countable really needed? Of course, it's open question, but I'm just curious if you have any thoughts.
I mean, I'm usually sort of very quick in voicing my opinion on these kinds of open questions. Some people are sort of much more cautious about only saying, I believe it's true if they've got good reason for why it should be true. But in this case, I just genuinely have no anticipation for what the answer might be. I kind of feel that whatever leads to the well, a kind of negative answer clearly would need to be weird. You would need to have all of those uncountable fibers without causing too much problems there. But then on the other hand, we know exactly basically where the clean O is coming from in the proofs that we have. So for basically each component, we know that each component of the proof is actually becoming false if we would try to do it while not having clean O there. So I kind of feel that the answer to the question will just look very different from anything I can imagine. And I can oscillate very quickly between believing that one option would be weird and the other.
Any other questions? All right, let's thank Arno again. And we will resume at 11:15 with Peter